disk access cost or a summation of those, all of those things, and then have possible costs for all of those formulations. The one that has the least cost would be executed then to make your database faster. And this is what your database does when it automatically decorrelates your query as well. So something that it sees, it plans over it. You know what? I don't need this for every loop. I can actually have it separately. So it designs that as a cost-based measure, and then designs this entire or restructures this entire query in that. Okay. So, so as I said, there are a variety of costs that are to be considered. The main primary cost is your disk access cost, right? If I can reduce my disk access cost, if I can write a heuristic or a cost-based planner that can reduce my disk access cost, then basically 70% of the job is already done, right? Then we also have some more smarter databases that look into CPU and memory requirements, and some other databases, for example, distributed database systems where your database is distributed across a network, right? We also need to consider the network bandwidth. Should I load or should I perform this join operation on my table, or should I send that table to this other server, depending upon the size of the table that is to be transferred, right? So we can consider all of those things when we are considering the cost of a particular query. Okay, so basically your optimizer has to consider several different types of questions. So how is your data stored in the disk? Is the access path available? Is there an index there? What are the possible relational algebra queries that are implemented by the database? So if you remember at the very first week, and I think we also had a homework on this, we said that we would like to find the maximum in a particular relation, right? So maximum number for an attribute in a particular relation. Remember how we performed a Cartesian product to actually find out the maximum, and we assumed that the maximum function was just not there, right? So even though a database uses a relational algebra model, not all things, maximum is usually available in all databases, but you can imagine that a certain thing is not available in all databases, right? So given the tools that we have in our relational algebra tool set, we need to figure out what paths would be the most cost effective, so to speak. Given the answers to those sort of questions, it is only then that we can decide, okay, we know that our database has this sort of things. How can we make our database faster? Because we know that it has these handicaps, right? Okay, so let's look at some particular operations to get a bit more idea about this. So let's start with the select operation. So a select operation is we filter out rows from your table, right? So we filter out, given a particular predicate condition, we filter out rows from that table. And we know that our data is stored in our drive or in our physical storage as heap files, right? So unorganized heap files. So the best way, or not the best way, the simplest solution would be to perform a file scan, right? Scan everything like a linear search, scan everything one by one, and then essentially return to me the rows that fit the query. This is a very generic solution for this thing. And you can imagine that this is not going to be a fast solution, but this is also a very flexible solution, because later down the line, we will see why, but this also allows us to select on any particular predicate that we want, right? I mean, any particular condition that we want, we can select on that, not specific to any particular equal to operator or less than operator and database designed for that, but we can actually use any particular query that we want. So most databases would have this file scan option in their toolbox, something that if not everything else fails, I can always do a file scan. that is slower, but that is also guaranteed to work, right? Okay. But we know that most select predicates do involve some sort of a binary comparison, right? So we know that most select operations either check with whether an attribute is equal to some value, whether an attribute is less than equal to some value, or something greater than equals to some value, and something like that. Now, if the data was ordered, we already mentioned that it is not, we are going to assume that it is in a heap system. But if the database was ordered, we could use something like a binary search to increase our speed. Now, if the database is not ordered, we will assume that it is a heap file unorganized system. Then for important attributes, what we can do is build indexes against your data file for those attributes, so that our linear file scan can be avoided as much as possible by cleverly building indexes for certain attributes that we know would be used, right? Okay. So then instead of performing a file scan, given that we have an index that is built either automatically in case of like a primary key or a foreign key, or explicitly by a user like create index, blah, blah, blah. In those situations, then you, instead of doing a file scan, your database can do something like an index scan, where it searches for the indexes available and then performs an index scan B-tree wise comparison results and so on. Right? Okay. So we talked about this last time. So then, given all of these possibilities, your query planner would then look at all possible access paths for a given particular attribute. So if a select predicate, so given the predicate that we are checking for, so if it's an equality test and the index is available for that particular attribute, your query planner would then say, you know what, instead of using a file scan, I would use an index scan for this, because that would make my life easier or make this query much more faster. However, for more complicated tests, or for example, if there is no index available for that particular attribute, we would revert back to a general file scan. Okay. So going back to our previous query. So your database would look at your query optimizer essentially would look at your select and predicate operations that you would have, see whether you have an index or not, apply those heuristics to actually figure out different plans that are faster. So if you remember, the heuristic was do select as early as possible to reduce the number of rows as fast as possible, right? So the previous join operation and the select operation that we had could be rewritten as something like this, right? So you know what, first perform the select operation, that is going back to this real quick, I'm sorry. So basically perform something like this, perform the second one. So perform a select operation first on the table T2, then perform a conditional join with T1 with the derived result, and then project it out. Since this select operation would result in smaller number of rows, I know that this join operation would become faster compared to joining this entire thing for every row. Because later down the line, I'm throwing away rows anyway. So if I'm throwing away rows anyway after that, why not throw away the unused rows first and then perform the join operation? Right, because a join operation requires us to loop over those things, right? Okay, so that is what this one does. So T2 would first be perform as we will first perform a select operation, and this is just one plan, right? So for T2.c equals to 10, T1, and then this derived result gets theta joined with b equals to b, and then we project out the result using a project operation. Now, given this plan, your planner then tags all of those planned nodes with the indexes that it has. It says that, you know what, for this select operation, I know that there we can, if we perform an index scan on T2, it would be possible because maybe there is an index on C. So if a database designer or a system designer built an index on C, then your planner would be able to use that and say tag it with that. So you know what, I will be able to use the C as an index. That would make my life easier. For this one, for column B, maybe T1 and T2 have indexes built on the column B. So it can then also tag that, you know what, perform an index scan on T1 because I have an index on B and I can actually perform this join operation like that. So your database would then tag all of those things. And once it has tagged with whether it's a file scan or an index scan, and for those every different types of plans, it would then compute the cost for each of those plans and then execute the one that is actually faster. Okay. Sometimes, most of the times indexes can be exploited, but sometimes, as you will see in your homework as well, I believe um, question number, no, no, not in the homework actually. We saw an example of this last class, right? When we built an index on balance, but it did not use that balance index, right? It just made a file scan. It did a file scan instead because that was faster. So there are certain circumstances where indexes cannot be exploited. More or less, indexes have to be exploited as low as in the abstraction layer as possible. So mainly we would like to have indexes being exploited in the physical level. When we are reading the data from the physical storage, that is where we would actually use indexes. As we go higher above the abstraction hierarchy, indexes don't have any uses because we are not doing anything, right? Because we are just getting combining results from derived relations that are already in memory. We actually want to use indexes that are in the physical storage. So that is why we applied an index on T2 here, possibly. We applied an index on T1 here for this join operation. But for this particular original plan, where we first performed the Cartesian product and then perform a select operation, the indexes cannot be used anymore because after we have performed the Cartesian product, we have this whole new table. There is no index for that table, right? We have not built an index for this derived table. So we have to go along without using indexes on top of that. So all of these things are taken into account for all of those plans. And then a cost is computed for each of those plans. And then we execute, or the database then plans and executes the one to plan, so to speak. Okay, so that was your select query. So essentially, the heuristic for select is do your select as early as possible. That is one heuristic, right? The project operation is the other one that we need to look at. So the project operation is quite simple, right? So the project operation essentially says for each input tuple, what is a project operation? We just project out certain attributes from that row, right? So if I just want the balance from my account table, I just project out the balance attributes. So we know that for each input tuple that your project operation gets, it would need to create a new tuple, but with only the attributes that are specified. So for each input tuple, there would be a new tuple, but with the specified attributes. It may also involve computed values, but more or less you would always have a tuple for those existing attributes. That also means that the number of rows that go in, that is the number of rows that go out. It is a smaller table in terms of the number of columns are reduced potentially, but the number of rows are still the same, right? So keep that in mind for a project operation. And now we can ask this question. Let's say that I have this query. Select balance from account where balance is less than 2,500 and project out all the balances. We can also look at the other version of this query is first project out all the balances from account